In this video, we will look at the concept of definite integral. Previously, we looked at the idea of finding the area under a curve of a function. Our example was for the function f of x equals x squared from x equals 1 to x equals 3. And we said that to estimate the area under the curve from x equals 1 to x equals 3, we use the idea of either calculating the area of lower rectangles or the area of upper rectangles to get an underestimate or an overestimate for the area under the curve. So if you recall our examples, or you can recalculate this yourself, the area of lower rectangles in this case was 5 units squared. The area of upper rectangles was 13 units squared, and therefore the average area between these is 9 units squared. And we also said that to improve the accuracy of the estimate, instead of having 2 rectangles, we use 4 or more. So we increase the number of rectangles. So when we increase this to 4 rectangles, the area of lower rectangles was 6.75, and the area of the upper rectangles, the overestimate, was 10.75, and therefore the average area between them was 8.75. So when n, the number of rectangles here, is 2, these are the areas. When n is 4, these are the areas. Now let's consider having 8 rectangles, n equals 8. We would find that the area of lower rectangles is 7.6875, and the area of upper rectangles is equal to 9.6875, and therefore the average area is 8.6875. What if we keep going with this process and we get to n equals 50 rectangles? So obviously here, as you can see in the diagram, the gaps between the rectangles and the curve are very, very small. They cannot be seen really. So therefore we're getting very, very close to the actual area under the curve. In this case here, the area of lower rectangles is 8.5868. The area of upper rectangles is 8.7468, and therefore the average area is 8.6668. So what can be deduced from this process here? As we increase the number of rectangles, we get closer and closer to the actual area under the curve. And as we increase the number of rectangles, the value for the area of the lower rectangles and the area of the upper rectangles get closer and closer to each other, and they zoom in on the actual area between the two, the actual area under the curve. So this can be expressed as follows. We say as n tends to infinity, where n here is the number of rectangles, as n tends to infinity, as the number of rectangles under the curve increase to infinity, the area of the lower rectangles tends to be equal to the actual area. But this is not how we write it. So we write the limit of the area as n tends to infinity is equal to the actual area, and the limit of the area of upper rectangles as n tends to infinity also tends to equal tends to the actual area under the curve. This process of finding the sum of infinite number of rectangles to find the area under a curve is known as the definite integral. The definite integral. So the area under the curve is the definite integral of this function. And it is written as area equals, in our example here, we were finding the definite integral of f of x. So it's the definite integral of f of x with respect to x between two limits. Our limits were from 1 to 3 in this case. Our function was x squared, so it's the definite integral of x squared with respect to x from 1 to 3. So this here is the symbol of the definite integral, and it basically means the area under the curve of f of x from 1 to 3. The definite integral of a function f of x from x equals a to x equals b is written as a, area, equals the integral from a to b of f of x with respect to x, and is represented graphically as the area between the curve of f of x and the x-axis between a and b. So if this is the value of a, this is the lower boundary of the integral, and this is the value of b, this is the upper boundary of the integral, then the integral from a to b is this area here, the area between the curve and the x-axis between a and b. This here is the area, and this is the value of this definite integral. So let's see how do we evaluate the definite integral of a function using graphical evidence. So here we are given a function. It says f of x, find the integral the definite integral from 1 to 5 of 3x plus 1. This is our function here. So let's graph the function y equals 3x plus 1. Now you can draw the graph of this function on the calculator and then sketch the graph, but you should know that this is a straight line that has a y-intercept of 1 and a slope of 3. So roughly the straight line will look like this. It has a y-intercept here at 1. The question is asking for the definite integral from 1 to 5. So 1 here is our lower boundary, so this is 1. And 5 here is our upper boundary, so this here is 5. Evaluating the definite integral is basically finding the area between the curve, or this straight line here, and the x-axis from 1 to 5. So our aim now is to basically work out the area of this shape here. Now, this here is a trapezium, and it's got two parallel sides. These are parallels. These are the two parallel bases, and this would be the height of the trapezium, or the base of the, or the the height of the trapezium. Since this is from 1 to 5, so this length would be 4 units. But then what is the length of this here? This would be f of 1. So when you substitute 1 into the functions, 3 times 1 is 3, plus 1 is 4. So this here is also 4 units. This length here is f of 5. So when you substitute 5 into the function, 3 times 5 is 15, plus 1 is 16. So now here, the area equals half the sum of the two parallel bases, which is 4 plus 16, times the height of the trapezium, which is 4. So this would be 4 plus 16 is 20, times a half is 10, 10 times 4 is 40 units squared. So the integral, the definite integral of this function from 1 to 5 is 40 units squared using graphical methods. That's using the known area facts or known area rules to find the integral. You can use the calculator to evaluate definite integrals to check your answers. So on the calculator, you go to options, and then F4 for calculus, and then F4 again for integral, and then the calculator will give you this symbol with a space, or with 3 different positions to write the function and the lower and the upper boundary. So we write the function first, which is 3x plus 1, lower boundary 1, upper boundary 5, and equals, it gives you 40, which is 40 units squared that we found. Another example, it says here, use graphical evidence and known area facts to find the definite integral from 0 to 3 of the function square root of 9 minus x squared with respect to x. Now again, you can draw this function on the calculator to check what it looks like. But again, you should know from previous years that the equation of a circle with radius, with the origin, with the center at the origin and a radius of 3 is x squared plus y squared equal to 9. So this is the equation of a circle with center at the origin and radius equals 3 units. So if I get the y by itself, so that would be y squared is equal to 9 minus x squared, and therefore y would be plus or minus the square root of 9 minus x squared. So y equals just the positive square root of 9 minus x squared, would give me the upper half of the circle, or the upper semicircle. So that means here this function is represented graphically as a semicircle with center at the origin and a radius of 3 units. So that means this point here is 3, and this point here is -3, and this is also 3. Finding the definite integral from 0 to 3, so from x equals 0, that's this here, that's x equals 0, to x equals 3, that's this here. So it's basically as if it is saying what is the area of this quarter of a circle here. So the area, which is the value of the definite integral, would be quarter of the area of a circle with radius 3, that's pi times 3 squared. So that would be 3 squared is 9, that's 9 over 4 pi units squared. That's if you want to leave it in the exact form. And again, we can check this using the calculator. So if I go again, options, F4 calculus, F4 integral, and the function is the square root of 9 minus x squared, lower limit from 0, upper limit 3, this equals 7.068, and this should be the same as 9 over 4. So if we check that, 9 over 4 pi, that's 7.6. So that is the value of the integral for this function. I'll show you another way to check the definite integral using the graphics calculator and the graph option on the calculator. So if you go to graph and then graph the function y equals 3x plus 1, so 3x plus 1, and let's change the view window so that we are able to see most of this graph here. So I'm going to go shift view window from, let's say, 0 to 6, and I'm going to go from -3 to, I need something above 16, so maybe 17 or 18. So this is the graph of the function. Now, to find the definite integral, you go to gsolve, and then you can't see integral here, so you go to the next screen, and then it's F3, integral. Now the calculator is waiting for you to enter the boundaries. So our lower boundary is 1, so you go 1, enter, and then waiting for the upper boundary, which is 5, enter. The calculator shades the area, and it tells you here that for the lower boundary from 1 to upper boundary of 5, the area is 40, which is what we found here before. And let's check the other function. So square root of 9 minus x squared, and change the view window. I'm going to do it from -4 to 4, and from 3, 2, 3. Notice here that you don't see a circle. That's because of the settings of the axes. If you want to get a perfect circle, make sure that you set the numbers on the x-axis to be double the range on the y-axis. So gsolve, next screen, integral from 0 to 3, and that gives us 7.068, and that's what we found before. That's this area here.